So, hello everyone, welcome to the next lecture, and sorry for the last lecture to be cancelled. I was sick and couldn't know this before. So today we're hopefully or maybe going to finish the section about the structure of the group of the points, of the rational points of an elliptic curve. So we in the last few lectures, we proved that E of Q has this structure because it's a finitely generated abelian group. And we have the Lutzner-Gall theorem that gives us an algorithm to compute the torsion points completely explicitly. So the missing link is only this z to the r. We call r the rank of the elliptic curve. And of course, we want to find out how large it is. We will, in this lecture and maybe also in the next lecture, we will work out an algorithm that gives us the possibility to compute the rank, but not in all the cases, but in most of the cases, so it's still useful. It's actually, there's no known algorithm that works for all elliptic curves, and there's also no known bound for the largest rank that exists. So this is still a big mystery. Okay, how can we compute the rank, and what do we need from the last lectures with this useful homomorphism that we constructed? I wrote down a few things that we used in the last lectures to keep them in mind. So we had the elliptic curve, and then we had a new elliptic curve that comes out of this one. We had this homomorphism. We had this way to write coordinates of points and then factor m in a way that we have some p's where the p's are prime divisors of b and some squares. And we had this homomorphism that lands in basically q modulo squares. But we will get to this and repeat this. So the important thing that we proved, or basically proved because we had some black boxes, is that the group of the double rational points is the image of this alpha, and this is isomorphic to this. We call it S. Okay, we had this in some of the last lectures and used this to prove that the index of E over E2E is finite. But now we don't want to consider only finiteness. We want to really look at what this R is. So let's write down what this is. Okay, I hope I didn't make any mistakes. So this looks like a monster. But what does it mean? So let's look at those things. If we consider we have this z mod p1 to the v1 over a modulo 2 z mod p1 to the v1, Well, if P1 is not 2, then this is just 0. So we only have to consider those Pi that are 2. Oh, this is so hard to write down. Oh, and today at 11 there will be a warning signal everywhere, so this will be the sign for our break. And maybe it also comes out of our smartphones, so let's see what happens. Okay, so we have to find out which PIs are 2, and we also have to find out how many 2s we have here. So for this we kind of go back one step. Yeah, maybe let me also write this down. This is also important. This is what I just said. Pj gleich equal to 2. So those Pi are the P's from the torsion part. So there cannot be too many. So we now consider the 2 torsion. So for just any point, since the group of rational points is finitely generated, we can of course find points in the free part. I take R that we add up. And points in the torsion part, I call them Q. Such that we can have Q as a linear combination of points from the free part and points from the torsion part. So if now Q should be a 2 torsion point. Maybe it's not good for copying. So if Q is a 2 torsion point, then of course twice this thing is 0. Or is the point at infinity? What does that mean for those Ni? So since the Pi come from the free part, they are not torsion points, so all the Ni have to be 0. And those Mi have to be, the double of them has to be 0 modulo the Pi where this is in. So if we have Qi is in the Pi torsion, pi vi torsion, then 2 times mi has to be 0 modulo pi vi. Okay, so this means for odd p, yeah, okay. Okay, so for odd p, we have, of course, or pi odd. We also have that mi is 0 modulo pi to the vi, and if p is 2, then it doesn't matter what m is. Huh? Ah, no. If p is 2 and we have this, then we can only say that mi is 0 modulo pi to the vi minus 1. Okay. So what does that tell us? Here we have no freedom to choose anything. All of them have to be 0 if we want to see what the 2 torsion are. And here we have let me write this down. We have 2 to the power of how many p's we have that are 2. Because we have this freedom of exactly if pi is odd, then this just means that mi is already 0 modulo pi to the vi, and if it's 2, then it's only 0 modulo pi to the vi minus 1. So we have 2 to the how many we have that are 2, different possibilities that will give us a point that is a 2 torsion point. Okay, what can we do with this? Since we have here basically the same thing, this means that this index is 2 to the rank times the size, it's of course like this, the size of the 2 torsion group. So in order, and since we in the proof of the Mordell theorem with this homomorphism, we know quite a lot about this. So what I want to say? No, forget what I want to say. So we have a link between this and this that gives us the rank of the curve. So we only have to compute this index and the 2 torsion point, 2 torsion group to get the rank of the curve. Now I would need a third board. Let me think about what I can erase. Okay, maybe I will will erase only part of this. Okay, so which elements are the rational points in the two torsion? We have, of course, the point at infinity. This is one. And all the other points that are in there have y coordinate 0. So since we have this form of our equation, since we want one rational point at 0, 0, we have that this can be 2 or 4, depending on how many other rational zeros this polynomial has. And this is only if oh, there's a typo, I think. Yeah. So if this is not a square, then this has only 0, 0 as a solution. And if it is a square, then it has 4 solutions. So we either have 2 or 4 points. So remember that we had our 2 homomorphisms from E to E bar, and this one from E bar to E bar bar. And what we also proved, so I will write it here, is that this index is the same as this one. Okay. So because we had that 2EQ is the image of the composition of those homomorphisms. Okay. So what we also have is, just because this goes from E bar to E bar bar, but E bar bar is just a variable transformation away from E. So E of Q contains psi of E bar of Q. And this contains the double points. And now we can just look at the indices. So this index that we want to look at wait. Yeah. So let's look at this, if this is correct. Yes, we just splitted this, so here and here is the same, and the rest is basically this, since this index over 2EQ is the same as if we put here psi composed with phi. This is what we have here, and we just put in between this psi of E bar, which is also okay because it lies in between there. So we just made smaller slices to make things easier. So the first thing that we want to compute is this thing here. And for that we start with an abstract remark that holds for any abelian group. The boards are just too small. We need more boards. Gesundheit. Okay. So this is independent of elliptic curves and holds for any abelian group. Let A be an abelian group. Be a subgroup of A of finite index. So finite index in A. Then we want a homomorphism of A into some group A. And now we want to compute the index of the images of A and the subgroup. So no, nicht mein Handy. So this will maybe also be an exercise. Yeah, I will write it down, and maybe it will be an exercise to point out which theorems are needed for that. But basically it's linear algebra 1. This will be an exercise, but what follows from this is if we now look at the sizes of the groups, that the index here is this index over this index. And this is what we want to use now here. Yeah. It's also easy to prove this for elliptic curves just by checking the formulas, because we have the formulas for this psi here explicitly, but this is probably not so nice. So we take this. So to what do we apply this? We use this for E bar of Q and phi of E of Q. So of course phi of E of Q is a subset of E bar, because this is just the image. So we can use this with A and B, and for psi we take psi. So what do we have here then? Okay, I'll write down everything. So this is just the first part from above here, and what we want to use now is this lemma for this. So psi is the same as here. A is this, and B is this. So we have A over B. This is E bar of Q over psi of E of Q. And below we have the kernel of psi over the kernel of psi intersected with phi of E of Q. Okay, so if we now go back here and remember from the last lectures, that we had this T bar, or is, is in the image of phi, if and only if a squared minus 4b is a square, and this T bar was just the kernel of psi. So the thing is, we want to find out how many elements do we take out if we restrict the kernel to the intersection of the kernel and this phi of E of Q. And what this tells us is that exactly when a squared minus 4b is a square, then this will get smaller. And if it's not a square, it will not get smaller. And so is a square, then the kernel of psi is the kernel of psi intersection with phi of E of Q. What happens if it's not a square? Then we just get rid of half the elements, and this index will be 2. And now the nice thing is I have not enough boards. So on one board that I already erased, we had that E of Q, 2 torsion point, is 2 if a squared minus 4b is not a square, and 4 if a squared minus 4b is a square. And so if we now put this in the other direction, this is 2r is E of Q, 2 torsion, over E of Q, the index, and 2E of Q. Then we see that, so in this index, we have here in the denominator a 1 if a squared minus 4b is a square, and so this will be here in the numerator because this is in the denominator and here again in the denominator. And in the numerator we have, if it is a square, then this is 4. And if a squared minus 4b is not a square, then this index is 2, and this size is 2. So again, the product is 4. So let me write that more clearly, maybe. We have this just from there, and then we put, yeah? Oh, yes. Yeah, thanks. Let me put this. No, I will erase it. Yeah. Thank you very much. Okay, yeah, now it's here also in the other direction. So we have this E of Q over psi E bar of Q times E bar of Q over phi E of Q. And now in the denominator we have this kernel thing. And the 2 torsion. So, and now what we have is, if a squared minus 4b is a square, then this is 1 times 4, because here's 4 and here's 1. And if it's not a square, then we have 2 times 2. So in any case, we have that this is 4. So it seems that it gets not easier, but it has actually already gotten easier. So instead of the 2 torsion and this index over 2, we have those two that we have to compute. And for that we have to go back to our psi and phi and alpha, our useful homomorphism, to find out what the images of those are, because well, this is about the image, this is about the image. And the question is, how many points do we miss with this phi and psi? And this is what we will compute now. And we will use, this will be about rational squares, because our alpha was basically about looking at things modulo squares. So now I think I can erase all of this. So this alpha was such that it goes from the rational points to the rational numbers modulo squares, and we had that alpha of xy was x modulo squares, and alpha of t was just the point 0, 0, was b, where this is this b, modulo squares. And now what we use is that the image, well, this is just the, I don't know what the name is in English, isomorphic theorem. Is this. And what we, I think, didn't prove but assumed as a black box was that the kernel of alpha is the image of psi. Huh? Ah, okay. Good. So what we want to compute basically here is the size of the image of alpha. So here we have this index of the rational points over the image of psi. This is just this size, and this is the same as this. So this is what we want to compute for now. And of course, what happens here is exactly the same thing. So here, just instead of E bar, we have E. Instead of psi, we have phi. So this is the same. And our alpha, of course, has also a corresponding alpha bar that just takes things in E bar. So the same can be done for phi. But then we have here E bar. And we have this. So the only thing basically that we now need to do is find out more about the image of alpha. The image of alpha is complicated because we look at this modulo squares. So we have to find out something about prime factorization, where we only look at primes that appear with odd multiplicity. But this could be pretty easy, at least easier than what we started with. And the question now is, which numbers can appear as the x-coordinate of rational points, and how does their prime factorization look like? And how many different primes can appear there with odd multiplicity? Because even multiplicity, we don't care, because we look at modulo squares. And for that, we also remind ourselves that we already proved that coordinates of rational points look like this. And since we only care for the x-coordinate, this is already pretty nice, because we can forget about this e squared. It's a square. Squares don't count for us. Maybe I should also, as a reminder, e is positive, and they're already in the lowest terms. Because we need this later. And if we look at all the possibilities for such an m over e squared, we can also see that for m equal to 0, we just get this. So yeah, this is all consistent. Yeah, we will see that later. Yeah, I think we will take a break here, and then we will also not have the warning signal in the recording, and meet again at 11:10. Okay? Good.